So remember, we were in the middle of proving this lemma, which I thought I would start writing. So let me finish this line. So Furstenberg's lemma is about probability measures on real projective space. Actually, I don't need real projective space. I just need a locally compact field here for my vector space, finite dimensional. And I'm assuming that I have a subgroup of PGLNR, which leaves this particular probability measure invariant. So two things can happen. Either the closure in this ambient group is compact, or there exists a V0 subspace of Rn, which is non-trivial, so it's not the whole space, and V0 is also not the zero space, such that mu of V0 is positive and has a finite gamma orbit. Okay, so when I wrote this down, I was stopped and asked what exactly is this bracket V0, and I hope people are feeling more confident with the projective space now. So V0 here is a subspace of Rn. Then what I'm writing for V0 is sort of isomorphic to the projective space of V0, except that I'm thinking of it as living inside of my P of Rn. Okay? And so what do I get from this conclusion? That my measure is supported on this or that it gives positive measure to this subspace, and gamma has a finite orbit. Yeah.
I was a question, but I realized the answer. You stated the theorem
slightly differently, yeah. It was because I was running out of space. So what I wrote last time was that there was a finite index subgroup that stabilized V0. So exercise that's equivalent to saying that gamma has a finite orbit. Okay. Exercise, yeah.
Is it possible for the measure V0 to be equal to 1, or is it
Yeah.
strictly less than 1?
Yeah, it could be everything, yep. Okay, so we were in the middle of the proof. It could be everything, yeah.
In which case, the finite orbit would be a
Yes, that's right. Okay, so so assume I'm just basically starting over that gamma is not precompact. Okay, that means that there is a sequence of elements going to infinity in PGL and R, and I'm going to find a lift to GLNR such that the norm on these lifts, which I denote by a tilde, is equal to, the definition of it is the max of the absolute values of the entries. Okay, everybody understand what I mean by that? And I'm assuming that this is equal to 1, okay? So the question came up, how do I know I can do that? And the answer was that the difference between PGLNR and GLNR are the scalar matrices, so I can rescale whatever number I get here, I can rescale it to give me 1. Okay. So, so this is a really important, clever step. A lot of Furstenberg's proofs are very clever. And actually, this has nothing to do with it, but I really wanted to mention Furstenberg's proof of the infinitude of primes. And you can look, there's a Wikipedia article on that, and it's pretty cool. So I encourage you to read that. So anyway, back to this. So I have this lift, and the maximum value of all the entries is equal to 1. And now I'm going to use the fact that M, N, R is locally compact with respect to this norm here. And so there exists a convergent subsequence, converging to G in the n by n matrices. Okay, so I have a convergent subsequence. I just threw everybody else away, and I'm keeping the label gamma sub n tilde. So what do I know about G? Well, I know that it has norm 1. So G is not identically the zero map. Okay. And I know that gamma sub n was going to infinity in PGLN R, which means that the kernel of G is not zero. Okay, so the fact that gamma n was leaving the space PGLN R tells me that I have a non-trivial kernel. Okay, so now I'm going to use the fact that both the projective space Rn and the Grassmannian are compact metrizable. To say what I'm going to say in this next board. I just put a question mark here. Last time when I was talking about the Grassmannians, I put an integer. That integer was supposed to be a dimension corresponding to, this is the question mark dimensional planes, subspaces in Rn, right? And why am I putting that question mark here? Because there's too many symbols already, and I don't want to give that thing a name because I'm not going to use it again. But this question mark is the dimension of this kernel. Okay? Okay. So, right. So I'm going to use compactness and metrizability of both of those in order to do the following. So first, compactness here gives me that gamma n applied to the subspace. I also wanted to put a tilde over here because I'm going to consider the projective version, and I want to keep my consistency and notation that everybody with a tilde is in G LNR, and everybody without a tilde is in P G LNR. So gamma sub n, now this is in P, of the kernel of G tilde, okay, converges to some subspace, which I'm going to call V, up to passing to a subsequence again, possibly. And why is that? Because of, so this is pointwise convergence in this space, okay? Is that clear? Okay, so, right, so where am I? Now the claim is that mu of V union the image of G tilde is equal to 1, okay? Is that right? Yes. V, I wrote that wrong, I think. Let's see. Okay, so so I have two subspaces, and their measure is going to be 1. And observe that that this is a closed set. Okay, now I'm going to call this A0. Okay? Okay. Kernel. Yeah, I'm pretty sure that's wrong. We'll see what's on the next page. Okay. So let's leave that here. Okay. So now I'm going to fix a metric on PRN. Okay. And I'm going to look at this function, which is going to be the distance. So it's going to be d sub a0 applied to x. This is going to be a map from P Rn to R. And it's going to be the distance between x and this closed subset A0. Okay? Okay, so now the claim is that dA0 of gamma n x converges to 0 for every x in PRN. Okay? And that will be true if I picked A correctly, which we'll see if we did, if I did. Okay. Also observe here that dA0 is bounded and continuous, which we're going to use at the end. Okay. Yeah, oh, and by the way, this is for Sundberg's lemma, but the reference for it is actually Shalom's paper. There's two papers by Shalom in the references, and this is growth dichotomy for linear groups or something like that. Okay, so this is almost exactly his proof. So, right, so now why is that? Well, what is happening to, I'm going to write, I guess I'll write it over here. So why is the claim true? Okay. Well, if x belongs to the kernel of G tilde as a subspace, then I have assumed that this whole subspace is converging to this space, which means that gamma sub n x is converging, is getting closer and closer to, let's put it this way. A0 is getting closer to V, right? This is by this. And on the other hand, if x does not belong to the kernel of G, then this is converging to the image of G. Then gamma n x is converging to gx, honestly, because G outside of its kernel is an honest linear map, okay, that I can projectivize. So therefore, which is in the image of G. And yes, I took my spaces correctly. Good. Okay? So all of these distances are going to 0. Great. So now I'm going to look at this projective space minus A0 and observing that I have this metric. This is going to be a union over M and N of the set of X such that the distance from X to A0 is bigger than 1 over M. Okay? So this is a closed set, so this is exactly, A0 is exactly the set of points where this distance function is 0. Can you hear me okay over the rain? Should I, higher? Okay, I actually talk pretty loud. I was gonna say there's chairs up here, but it's not true. Okay. Okay, so, right, so what I want to show now is that this countable union of sets has measure 0 by showing each one has measure 0. So the claim is that the measure of AM, which I did not define, is having measure 0. So this one here is called AM. Okay, so A0 is where the function is 0, and AM is where it's bigger than 1 over m. Not quite the same, but okay, so the measure of AM is equal to 0. Well, what do I have? I have that the measure of AM times 1 over m is less than or equal to the integral of this function over the set AM. Right? Which is less than or equal to the integral over the whole projective space, A0 of x. Right? And now my measure is gamma invariant, which means that, so I'm continuing this line over here, that this is actually equal to the integral over P of Rn dx0 x d mu of gamma n inverse x. Okay, this is the push forward of mu under gamma n. It means it becomes the inverse when I go inside. And now when I do the calculation and the change of variables, this gamma n inverse x is going to become a gamma n here. Gamma n x d mu x, okay? So this was a less than or equal to, this was a less than or equal to, and otherwise I have equality. And now this is a continuous bounded function. Well, it's a sequence of continuous bounded functions that converge to 0. So I know this is forbidden, but I'm just going to write an arrow with a 0, okay? And by the dominated convergence theorem, this converges to 0, which means this set had measure 0, which meant this set had measure 0, which means that the claim I wrote and erased is true, namely that the measure of A0 is identically 1. Okay? Good? Great. Okay, so that's almost what I promised you, but not quite. What did I promise you? I promised you one subspace of measure 0, of positive measure, and I have given you a union of two things of positive of measure 1. Okay? And I also promised you that some particular subspace would then have a finite gamma orbit. Okay? So I still owe you those two parts. Good? Okay. Okay. So now, to finish, let me write down what we have so far. So far, we have that the measure of, let's say V union W is equal to 1. Where W is the image of G tilde, okay? it doesn't matter exactly at this point who it is. I've produced a union of two subspaces that carry the measure, okay? Scary. Okay, so now I want to produce a particular one that has positive measure. So to do that, we're going to let V0 be a minimal dimensional subspace such that mu of V0 is positive. Okay, so how do I get from here to here? Anybody? So I know that I have two subspaces of total measure 1, okay? Well, one of those has to have measure at least a half, right? So in fact, I know that I can have some subspace with measure at least a half, and I'm just saying pick a minimal one that has positive measure. Okay? Everybody clear on that? Okay. So now, what can I say about gamma V versus V0? Okay? Well, I know that that mu is gamma invariant, which means that mu of gamma V0 is also positive, right? It's gamma invariant. And what can I say about the intersection of two subspaces? What's the intersection of two subspaces in a vector space? It's another subspace, right? So since the intersection of subspaces is a subspace, it follows that the measure of gamma V0 intersect gamma V0 is 0, okay, oops, or gamma V0 is equal to V0, okay? So now why is that? Well, what's the dimension of this thing, assuming it's not 0 or empty? It would be less, right? Can it have positive measure? No, because I took a minimal dimensional one, right? So therefore, either they're equal or their intersection has measure 0. And then I have a positive measure thing whose intersection, the translates either have measure 0 or they're equal. And so the conclusion is that the orbit is finite, i.e. there is a gamma 0 in gamma of finite index stabilizing V0. Okay? And that's the end. Oh, it's kind of warm in here. Is it possible to do something about that? Or maybe we can just open the door or something. Okay, so that's the end of last time's lecture. Any questions? Okay, so okay, so the reason that this came up was because I was trying to get us to what we're going to talk about next, and that was the question, if I know I have an amenable group that's a subgroup of, say, PGLNR or GLNR, then what can I say about that group? Well, it would need to have an invariant measure on projective space, and that would give me this conclusion, okay? So let me actually write another conclusion. So we got to this lemma via the question, if gamma is in, let's say, PGLN R, is amenable, what can we say about gamma? Okay, what does that imply about gamma? Well, so far we've seen that it has to have a non-trivial subspace, so a non-zero, not full subspace that is virtually stabilized. Okay? So if I have such a subspace, I'm just going to kind of write out an argument. So by Furstenberg's lemma, which I'm abbreviating First's lemma, there exists a gamma 0 finite index stabilizing V0, okay? Which means I can quotient by V0, and I get a new representation. Then I can look at the quotient representation. Gamma maps to PGL and R, or now I have to put gamma 0 because V0 is not gamma invariant. Gamma 0 maps to PGL of Rn mod V0, okay? Rn is a vector space, V0 is a vector space. I can take quotients of vector spaces. I get an induced representation by the fact that gamma 0 was stabilizing V0. If I were to, is this familiar to everybody? No? Okay, thank you for being honest. Okay, so if I, here's the sort of quick picture, okay? If I stabilize, so I'm talking about gamma 0 now. If I stabilize V0, then I can choose a basis of V0 and extend to Rn, okay? So V0 is a subspace. I pick a basis for it, and then I extend it. What does gamma 0 look like in this basis? So now I've changed my basis, new basis, and I'll write it over here because I know I'm getting low there. So with respect to this basis, gamma 0, so is, let's say, conjugate into this basis, like it looks something like this. It has a V0 block here, it has a 0 here, and it's a star and a star here, right? Because it has to take the first however many vectors I had for V0 to themselves, which means that I have zeros here, right? So what does it mean to look at the quotient representation for GLRN mod V0? So what does it mean to look at this quotient representation? It just means I'm killing off that first block row, okay? Is that good? Yes. So this becomes this, okay? So that's very sketchy, but it's a nice picture, and it's true, and exercise, okay? Okay, so now I have this representation. Now, what do I know about the image of gamma 0 in this? Is it amenable? Yes, because you did the homework that said that the quotient of an amenable group is amenable, right? So it's still amenable, okay? So it has an invariant, measure on the corresponding projective space, right? And now what am I going to do? I'm going to repeat, right? So the dimension here is less. It's finite dimensional. This will terminate in finitely many steps. And so what is happening at each step? At each step, I'm either getting something that has compact closure or that stabilizes a subspace where I'm applying that, where I'm applying the sort of inductive step, okay? So at the end of the day, the answer to this question is so the answer is that you can have gamma will have, this is in the projective space now. If you lift it, you might have like diagonal things. So gamma is going to be, gamma contains a finite index subgroup It's not the same as the gamma 0 over there, so let me call it gamma prime, which is conjugate into something of a block, upper block triangular form, where here I have compact, 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 and then sort of whatever you want on the above the diagonal, and zeros everywhere below the diagonal. Okay? Good? Yeah.
Does this method allow to compute the index of gamma 0?
Probably, because everything is fairly constructive. You know, you have to look at these limits, and I think so. Yeah. Go find out and let me know what the answer is. Other questions? Yep. Yeah, so let me assume that this star is 0 for a minute. Where did you go? There you are. Assuming that this is 0, an example would be like SO2, the special, so there's like a circle, right? Cross SO, let's see, 3, okay? So this is compact, this is compact. If I had zeros everywhere else, which I didn't write down because they're 0, this is isomorphic to the product of SO2 with SO3, okay? Otherwise, on the upper block diagonal, if I have something there, then it will be a semi-direct product of this product with this solvable group that is kind of living on the off diagonal. Okay? So what I mean here is I have a compact Lie group, okay? Like the identity. I could have put another, I might have a block in here which might be like a 1 block. It's 1 block that is nothing. A boring block, okay? Questions? And then again, this is in, oh, I didn't write that down. This is in P, G, L, and R, okay? If I forget my P, then in these boring blocks, I might have diagonal entries. I might have like lambda, 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 lambda on the diagonal, okay? Okay, questions? And also, by the way, this is amenable. And this is an amenable group. Locally compact. Second countable group. Okay. Other questions? Okay, so I guess I am still not going to start what I thought I was going to start talking about today, because I feel I should mention the Tits alternative and maybe not lead you astray with this conclusion here. So gamma was supposed to be amenable, and my conclusion was that the closure was amenable, okay? But let's just very quickly mention the Tits alternative. Okay, so gamma is a subgroup of, say, GL and R. Then either gamma contains a free group, which is equivalent to containing F2 exercise, or gamma is virtually solvable, i.e. has a finite index solvable subgroup. Okay. Now, why do I mention that? Well, it's related to the Banach-Tarski paradox, which we're going to hear about later. But specifically, here, I started with the assumption that gamma was amenable, and my conclusion was that the closure was amenable. Okay? The converse is not true. If my closure is amenable, I don't know. Specifically, I guess I'll say it over there. So, warning, F2 is not amenable, which you proved, and it embeds into SO3 as a dense subset, subgroup. And so just because my closure is a compact group, just because my closure is amenable does not mean I am amenable, okay? So when you're dealing with locally compact groups, you have to say closed for whatever subgroup property you want to talk about. Okay? Okay? Okay. Okay, so no more questions about that. Relative property T. And semi-direct products. Okay, so what is a semi-direct product? You've probably seen semi-direct products before. I'm going to remind you. So I'm going to take a group, and aught A, it's a set of alpha from A to A, such that alpha is an isomorphism of A, okay? And gamma is a group. And I'm going to take phi, a representation of gamma, into the automorphism group of A, and I'm going to use this to form a semi-direct product. So for now, I'm going to decorate my semi-direct product with the representation phi, but I will very soon stop doing that. Okay, so this is going to be a group. So if I'm going to tell you something is a group, I have to tell you what it is as a set, and then I have to tell you what its multiplicative structure is. So the set is easy. It's a product, but it is not a direct product in the group theoretic sense, and that's why I have this kind of funky-looking cross, okay? If I cover the tails, it looks like a normal subgroup sign, right? So that means there's two ways of describing a semi-direct product. There's the sort of this way, and then there's the that way, okay? I'm going to do this way, and some people do this way. In fact, kind of depends on your area which one is more common. But you should know which one is which because it's pointing toward the normal subgroup. So you won't make that mistake, which a lot of people do, actually. OK, so it is a set. As a set, it is that. And now I'm going to tell you the multiplicative structure. Now, I could, a set is, of course, pairs gamma, comma, A. I'm not going to write gamma, comma, A because I think it's more confusing, OK? So I'm just going to write gamma A, and then I'm going to multiply that by eta B, OK? And I need to express that in a form of something in gamma, comma, something in A, or something in gamma followed by something in A. So here, of course, gamma and eta are in gamma, A and B are in A. OK, so what I'm going to do is a pretty standard trick in group theory, which is to multiply by an element and its inverse. OK? And now I have here what looks like conjugation. And I told you that this was supposed to be something where A was like a normal subgroup. OK? So if A was a normal subgroup of my group, I would know exactly what this was. But I don't know what it is because I like creating a group. So I need to tell you what that is. And that is going to be gamma eta of phi of eta inverse applied to A. Yeah, let's do it like this. OK? So this is something in gamma, capital gamma. And this is something in A. Do you agree? OK, now you can do the same thing with the Cartesian coordinates gamma, comma, A. But you're going to have all these parentheses and commas, and they're going to be very confusing. OK? So notice I have this inverse here. OK? Check me. Does this work, or did I put an inverse incorrectly? OK? Exercise. OK. Yes. So that's a group structure. Oh, yeah, observe that if N starts off as a normal subgroup of G, then G acts on N by conjugation, right? Exactly saying that the N is a normal subgroup means that when I conjugate, I blend back an N, which means that whenever I have a normal subgroup, I get a representation of G into the automorphism group of N. This is always true. Does that mean all groups are semidirect products? No. OK? What's the difference between being a semidirect product and this observation? Well, the difference is that I can't always put a product structure on what I have. OK? So in order for, right, so I think I'm getting a little carried away with this. But let me finish. So being a semidirect product exactly corresponds to finding a homomorphism sigma. So if I have a normal subgroup N, I can take its quotient, and I get a quotient group called Q. And now this gives me a short exact sequence. And so my sigma is going to be sigma here. I called it sigma for a section. Sigma is a section. I can always lift anything here to some representative over there, but I'm asserting that if this is a homomorphism, then So sigma homomorphism, there exists sigma homomorphism if and only if G is a semidirect product of Q with N. Okay? Okay, that was too much time spent on semidirect products, but I really like them. They're a lot of fun. Okay, questions? Okay. So now I promised you relative property T on semidirect products. Now we're going to actually talk about relative property T. So recall a definition I gave yesterday. I have pi, a unitary representation of a group G, which is strongly continuous. Okay? I'm saying it's strongly continuous so that you don't take away my math license, but in the end of the day, it doesn't really matter for what I'm going to write down. If I hadn't written strong continuous, then you would know that I was talking about a discrete countable group, and I probably would have written a gamma here. But we are going to be looking at locally compact groups now. Strongly continuous means the product map, the action map is continuous. So I have a nice unitary representation, and we say that pi has almost invariant vectors, and we write pi, funny little squiggly, bigger than or equal to I sub g. I sub g is the trivial representation where everything acts as the identity. So pi has almost invariant vectors means that there exists a sequence of vectors hn, vn, which are non-zero, so that pi of gamma vn minus vn divided by vn goes to 0 as n goes to infinity. That's actually what I wrote last time for the discrete countable group, and then somebody was like, don't you want for all gamma? That's probably true. If I didn't do it there, I did it somewhere else. So here I could put for all gamma, but now I'm in this new locally compact second countable situation, so I need to be a little more careful. So here this is going to be the sup, or the max, over gamma in K. What's K? A compact subset of G. Okay? So, yeah. What is a compact subset of a discrete countable group or set? Finite, right? So actually, when I gave you this definition, I said pointwise for each element. If this was really the same, I would have said for every finite set. Agreed? So, exercise. Yeah? Namely, show that what I gave you yesterday is equivalent to this, where G is discrete countable and K is finite. Okay? Okay. So that's what it means to have almost invariant vectors. And now I want to tell you what it means to have actual invariant vectors. So, and recall, pi has invariant vectors if there exists a v and h such that pi of gamma v equals v for every gamma in G. Well, that would be not very interesting if I didn't throw away the zero vector, because the zero vector is always a fixed vector. So when I say invariant, I'm really saying non-trivial invariant. Okay, non-trivial fixed. Okay. So definition, G locally compact second countable, H and G closed, okay? We say G comma H has relative property T. And somehow that is just way too long for me to write, so I will often write it rel T, okay? If whenever pi is a unitary representation of G with almost invariant vectors for G, then pi restricted to H has H invariant vectors. Okay, so that's 3 definitions all right together. So what's this saying? Oh, sorry, I wrote in the forbidden zone. Everybody good? I could rewrite it up here. Is it okay? Okay. So what does it mean to almost have invariant vectors? Well, here, this is a G representation. So I'm saying G almost has invariant vectors or has almost invariant vectors. So it really looks almost like there's things that are preserved. Vectors that, yeah?
I don't know if it's clear enough for everybody that the symbols are.
Yeah. Oh, they're too curly. Yeah.
One more curly.
Is that?
So really it should be clear that it's not the same symbol.
Yes. Thank you. Okay, those are not the same symbol. This one's curly, this one's not curly. So this one is curly. The curly one is saying, like, it almost is like this, okay? So this is a property for a group pair G comma H. And it's saying that if G almost looks like it has invariant vectors, then I definitely have H invariant vectors, okay? So it's like a relative rigidity. If I can look like I perturbed the trivial representation for G, then I actually have really invariant vectors for H. Okay? Okay. So as an example, which you won't be able to see right away, but we're going to prove it. So example. SL2Z semidirect product Z2 has relative property T. Okay? Yep. So property T, which we're going to get to soon, is where G comma G has relative property T, which means that any unitary representation of G with almost invariant vectors actually has honest G invariant vectors. Yeah? Yeah. Good question. Okay, so S has relative property T. We're going to prove this. We'll prove. By the way, my X is not exercise, it's example. Okay. Non-example is an exercise. So gamma, discrete countable, is amenable. And H is a subgroup of gamma, is infinite. Then gamma H does not have relative property T. Or alternatively, if I have an amenable group with a subgroup giving me relative property T, then that subgroup should be finite. So exercise is to prove this. Okay. Well, let's quickly talk about it. What do I know about amenable groups? Probably too much. I gave you like 20 definitions, and you probably don't remember most of them. There was one that was related to this, right? Because actually, I gave this definition yesterday, didn't I? Did I give it for a general pi? Yes, I did. Did I apply it to a general pi? No, I didn't. What representation was I talking about yesterday? The left regular representation, right? So I have a left regular representation with almost invariant vectors if I'm amenable. Now finish, okay? Okay. Questions? Okay, so let me give another reference. If you want to prove that this directly has relative property T, direct proof is interesting. It's sort of computational in nature. And this is by Shalom in the bounded generation paper. And actually, that's not quite the, maybe it's called bounded generation and Kazhdan constants or something like that. It's going to be the other reference in the references on my homework sheet. But we're not going to take that route. It's more complicated. We're actually going to take a different route, which is going to, so I'm talking about the proof of this. So example, let's call it a theorem. So we're going to take a different route to prove this theorem. Okay? We're going to show that SL2Z symmetric product Z2 with Z2 has relative property T if and only if SL2Z symmetric product R2 has relative property T. Okay? And the fact that this is a vector space is just going to make the calculation, or whatever, not the calculation, but the proof simpler. Okay? And in particular, we're going to use Furstenberg's lemma. Right. Now, why is this true? Well, what's the quotient of R2 by Z2? A torus. Is the torus a group? Yes, it is, because it's a quotient of a group by a normal subgroup, right? And it's, in fact, a compact group. So compact groups have property T, which brings us to what property T is. So I think I'm skipping. Nope. OK. So G has property T. OK. If GG has relative property T, i.e., whenever I have a unitary representation of G with almost invariant vectors, that was too curly, it means I have invariant vectors. Okay? I.e., whenever I look like I'm close to having invariant vectors, I really do. Okay? Example. example/lemma. Okay. G compact, then G has property T. Okay. Again, property, just too many letters. I'm abbreviating it to prop T. G compact, G has property T. Okay. Okay. So why is that? The idea. So what have you learned today or possibly before about compact groups? Har measure. Huh? Maybe you didn't. Okay, so idea. I actually wasn't at the little mini lecture. So G is okay. Recall / look up if you don't already know it, that G is locally compact. Second countable. Then G has a left invariant Har measure. Okay. And what is the left invariant Har measure? So the real numbers is a locally compact second countable group. What's the Har measure on R? Okay, good. Yeah. So I have a left invariant Har measure on G. What's the Lebesgue measure on R? Does it have finite measure? No, right? So G is compact if and only if the Har measure is finite. Okay? So using Har measure, you can average vectors. Well, okay, using finite Har measure, you can average vectors and get an invariant vector. Right? So what's an example of Har measure that's finite? Well, I could have counting measure on a finite group. So assume G is just a finite discrete countable group. Finite discrete group, okay? Then counting measure, counting is a G invariant measure on G. Okay? So what I can do is I can look at my unitary representation and assume pi has almost invariant vectors. And then I'm going to pick an f that v non-zero that is almost invariant, whatever that means. I'm not really proving this. And what I'm going to do is I'm going to average pi gamma v over v gamma in my now finite group. And I said it was an average, so I should maybe divide by the cardinality of G. Okay? So is this vector G invariant? What do you think? Yeah, right? Because if I hit it by G, then I'm just permuting these finitely many elements. So it's definitely G invariant. So have I won? What's the problem? it could be 0, okay? So is this not 0? So that's where you're going to have to work a little bit. And that's where this notion of almost invariant comes in, that you're going to have to argue that when you're averaging things, they're staying sort of close together. So their average is going to be close together rather than, you know, this being the vectors that you're looking at, and then their average is in the middle, being 0. Okay? So the almost invariant means that you're not moved very far. So or you can find vectors that are not moved very far, and so you have to find one that's like that. Okay? Okay. So property T groups have, compact groups have property T. And so, yes, so exercise. Assume that H has property T. Okay? And H is a subgroup of G is closed. Then prove that GH has relative property T. Okay? This should be pretty easy if you understand the definitions. Okay. Questions? Okay. So lemma. Suppose that, okay, everybody is a group here. I have a short exact sequence. Whoops. And I have a representation of a group gamma into the automorphism group of A that stabilizes A0. This is the subgroup of aught A that stabilizes this normal subgroup called A0. Okay? So I just call that aught A, comma A0. Now, we have that gamma semidirect product A0, comma A0, and gamma semidirect product A1, both have relative property T. If and only if gamma semidirect product A has relative property T. Okay? So I have a short exact sequence. If the thing on the left and the thing on the right with gamma give me relative property T, then the thing in the middle with gamma give me relative property T, and conversely. Does it look familiar? I put something almost exactly like that in yesterday, but it was without the gamma, and it was about amenability, right? Okay. So, okay. I was gonna, yes. My what? This one? Yeah. The definition? Yeah, so aught A is the isomorphisms from A to A, and this is the one that stabilizes A0. Why did I write that down? because I want this to make sense. Okay? And if it makes sense, then it's this, then this one will also make sense. Right? Good question. Okay. So I was going to put this as an exercise, but I only have a few more minutes. So maybe let's just like walk through how this goes a little bit. Okay? So I'll just start proving and see, and then see how far we get. Okay, so let's suppose, so proof, or at least part of the proof, assume that A0 and A1 give me relative property T. Okay, does that make sense? I don't want to write that down again. It's too long, right? So I'm assuming this part, and I want to conclude this part. Okay, so assume this. Now, let's prove that gamma semidirect product AA has property T, relative property T. And I'm going to do that by looking at a unitary representation of my group with almost invariant vectors. Okay? Well, what can I do? Well, observe that this contains this subgroup, right? This is a subgroup of that group because A0 is a subgroup of this, and gamma preserves A0. So that means that this is a representation of gamma semidirect product A0 with almost invariant vectors, right? This means that it's very hard to think when you're under the clock. So this means that there exists a V in H, which is not 0, and is A0 invariant. Yeah? Okay, now I have like 5 seconds, but I'm going to take like 1 more minute. So what do you want me to do with this vector? So where am I? I have this short exact sequence, right? I know something about the ends of the short exact sequence, and I want to conclude something about the middle. And I just concluded that this vector is A0 invariant. So now what?
It would be take its orbit and then the quotient will act in that orbit.
Yes. Very good. So take the orbit and the quotient will act on that. What will the quotient be? Well, A0 is acting trivially, so it will be gamma semidirect product A mod A0, which you then have to prove is actually gamma semidirect product A1. And now I'm done? No? I need to apply my hypothesis to this group. That means I need to know the hypothesis holds. Right? What's the hypothesis? The hypothesis is that I have almost invariant vectors. But maybe when I looked at this orbit, my almost invariant vectors got left behind, right? But they didn't, and that's an exercise. Okay? So thank you very much.